Hello, Physics Nation. My name is Nate Larmond, and this is the video you've all been waiting for. It's the spreadsheet video. We're going to input the fall distances and fall times from this experiment. I switched up the way the document looks a little bit. I thought Galileo and the Leaning Tower of Pisa with the heavy object and the light object is a cool historical reference. Interesting that Galileo wanted to manipulate mass of his projectiles. This famous demonstration is manipulating the initial horizontal velocity, the drop ball and the shot ball, and we are manipulating the drop height. So sort of three different versions of the falling object. Anyway, um, here's our original data set. This is what I wrote down when we were in the backyard. And like I said, it's spreadsheet time. So we're going to do average velocity equals distance over time. Final velocity is double the average, and then acceleration is the rate of change of velocity. That is the final velocity minus the initial velocity divided by time, except the initial velocity is 0. So it's really just the final divided by the time. Sounds complicated, but it's not. All right, so I've already sort of started the spreadsheet. Here is fall distance measured in meters. And let's wrap text. Where's the text wrapping? Here we go. There we go. Let's merge and center this. Merge horizontally. Let's center that. There we go. Okay, so fall time is in seconds, and then we have our individual times. Let's find the average. So equals AVERAGE, open parentheses, click and drag. Oh man, am I in the wrong row? Shoot, yes I am. All right, well, that's a bummer. Let's fix that. Oh, no, that's it. That's where I want to be. Okay, cool. So now I can just autofill. There we go. That's beautiful. We just found the average. Now, equals, we're going to do distance divided by time. All right. And we fill that down. And then we double the average velocity, this guy, multiplied by 2 to find the final velocity. So that's how fast the ball is going when it strikes the ground. And finally, we find the acceleration. So equals final velocity divided by average fall time. And how'd we do? Ooh, okay, a couple runs were good. The actual acceleration, oh boy, I can't spell acceleration, is n, all right, equal, whoops, n, and we can find the percentage error, just for fun. So equals, open parentheses, the experimental value, subtract real value, close parentheses, divided by the real value. So that's kind of rough. How did I do here? Let's change these guys into a percentage. That's interesting. So the actual question I'm asking is, how does fall distance affect acceleration? That's the official graph we're supposed to draw. Insert chart. Not a column chart. A scatter. And that's a pretty horrible set of data. It's supposed to be a nice horizontal line at 10. This is interesting. Interesting to me anyway. Let's do a trend line and let's get some labels on these axes. This is acceleration. Oh boy. Acceleration as a function of drop distance. And the horizontal axis is drop. Oh no. Drop distance in meters. And the vertical axis is acceleration. Acceleration in meters per second. Well, what can I say? You win some, you lose some. Like I said, it's supposed to be a horizontal line at 10.